In our last lesson of Module 2, we're going to explore some more ways we can use our setParameterByName command, building off of the code we wrote in the last lesson. We'll also be taking a look at a method we can use for detecting the material a player is running on to adjust the sound of the footsteps accordingly. First, let's quickly get a recap on what we set up and learnt in the previous lesson. In FMOD, we made an event that, when called, will play a footstep on a particular surface, which can be changed when the material parameter is adjusted. We then set up a function to create an instance of it, play it, and destroy the instance all at once. And finally, we created two animation events for the running animation of our player, which we used to pass our event into our function and trigger it to play from. All of this combined into a simple and effective way to play footsteps for our character, meaning it's now time for us to see how we can improve this system and change the material that we hear. So the first thing we are going to do is create new tags, one for each material that our parameter can change. Now, if you remember back to the play one-shot lesson, we learned that we can use tags to label our game objects and then interact with them in our code. Well, in this lesson, we'll be assigning the tags that we made to the surfaces that the player can run on top of. Then once the game is running, we'll be using our code to detect the tag of the current surface they're running across. So to create a tag, we need to go to the Tags and Layers page by clicking the Edit tab at the top, then scrolling down to Project Settings and selecting Tags and Layers. If we close the Layers tab from last time and open the Tags tab, we can see all of the tags that have been created by the developers of the 3D game kit, which is only one called FlyThroughCam. Now, if we want to add our own to the list, we simply click on the plus symbol here and type the name of our tag. Let's call our first tag Earth and give that a save. We can now assign this tag to the game objects within our scene and the prefabs inside our asset folder. First, let's create 3 more tags for the rest of our material sounds. We're going to create one called Stone. We're then going to create one called Puddle. And finally, we'll create a 4th called Grass. Now it's time to add these tags to the surfaces we'll be running on. However, this is also the time-consuming part, as there are a lot of objects that our player can theoretically run across. For this lesson, I'm going to just be adding tags to 1 or 2 objects just to demonstrate, but feel free to add more to other objects to get the full effect of the footsteps changing sounds in this level. So the first object I'm going to assign a tag to is this muddy terrain our player is currently on top of. So if I click on the object in the Scene tab and then come over to where it says Tag underneath its name in the Inspector tab, I can now click on it and I can assign one of those material tags we created earlier. So I'm going to give this the tag of Puddle. If I then move the camera over to the stone steps over here, I can get close to them, click on them, and again, I can assign them a tag. So I'm going to give that stone and then the steps as well. I'm also going to tag with stone. Now, whilst we've got this object selected in the game world, we can actually also access its prefab by clicking open here. And as you can see, it's not been tagged. So we can quickly give that a tag. And now whenever this object is loaded into other scenes, it will have this tag ready to go and we'll be able to interact with it with our footstep sounds. So I'm now happy for the moment with these tags, and hopefully you've added tags to these objects as well to follow along. If you have, then we're ready to jump back into our footstep script from the last lesson and learn how we can detect these tags. So as you can see, we're picking up right from where we left off. The first adjustment we need to make to our script is the addition of a new function. So let's quickly make some space in our script. Let's write void to declare the function, and let's give it a name such as material check. Let's also add its parameter brackets and give it a body. Next, we're going to need a new float variable that we can use both in this function and play run event function. So at the top of our code, let's quickly make some more space. And let's write private float and give it a name such as material value. Finally, we want to call the new function we created, material check, inside the one we created in the last lesson, play run event. Specifically, we want to make sure we do it before we create an instance of our event and tell it to play. So on the first line, we're just going to write the name of the function we want to call and give it some parameter brackets. There we go. So the idea is that we're going to use this function to set the value of our material value float, which will control the FMOD parameter we created in the last lesson called material. This will be done every time we call the play run event just before we tell our footsteps to play. And later we'll be feeding the float value directly into our parameter and our event instance, but for now, the first thing we need to do is use what's called a raycast to find those tags we created. Now, a raycast is basically an invisible line that could be sent or drawn from any object in our game into the space around it. They could be used to detect other objects that they come into contact with or retrieve information about that object for us to use. In our case, we want to fire a raycast from our player character straight into the ground until it hits a surface we are running on. Now, when it comes into contact with that surface, we can then use it to tell us what tag is labeled to that surface. To create a raycast, we simply write in our function physics.raycast with 2 brackets. Now, inside these brackets, we can feed this raycast function 5 arguments, the first 3 of which are mandatory and must be included for this to work, but the last 2 are optional. And the first thing it needs is a vector 3 to tell it at what coordinates it should start the line at. Now, in our case, we want the line to start at whatever position the player is at, so we'll use our shortcut for getting our transform component by writing transform with a lowercase t in the brackets, and then access the position coordinates inside that component by using the dot operator and then write in position, in the exact same way we've done with our play one-shot commands. Next, we need to give it another vector 3, but this time to tell it in what direction we need to send our line out into the world into. Now, so far, we've only used vectors for positions and not really directions, so let's quickly give our command a new vector before we talk about how to use them for a direction by separating this argument with a comma and then writing new vector 3, and then just giving it zeros as the coordinates. Now, as we learned from the play one-shot lesson, each value in a vector represents the x, y, and z axis respectively. If we were to replace one of these zeros with a number, we'd be telling our code to draw the raycast in the direction of that axis. So for example, if we set the first value to 1, we'd be drawing our line on the x-axis. The size of this number also determines the distance that it travels. So let's say, for example, that our player is standing somewhere in the world and Ellen's positional x-coordinate is 4. By writing that number 1 in our vector, our line will be drawn from 4 to 5 in the x-axis. If we replace that one with a 2, it will be drawn from 4 to 6. So going back to our desired outcome, we want to send this line directly down towards the ground so that we can then detect the material we're walking across. Now, in order to do that, we'd simply change the middle 0 we've written here, which we know represents the y-axis, to a -1. And by writing minus numbers, we are essentially telling our line to travel in the opposite direction that the axis travels in. If we put a positive number, then the line would travel up the y-axis towards the sky. So by writing -1, we're making sure that it is sent directly downwards. Now, thankfully, Unity actually has some pre-programmed shortcuts built into its API to use as directional vectors, saving us from creating a new one in our code. So let's remove this new value we created and instead write vector3.down. And as you should be able to see from the small text here, it's essentially exactly the same thing as we wrote. The x value is 0, the y value is -1, and the z-axis is also 0. And there are others for you to choose from. There's up, there's down, there's left and right. And I'll also have a link under this lesson for you to see all the different directions and their corresponding vectors. Next, we need to feed the information our raycast receives into a variable with the data type raycast hit. So let's quickly create that variable at the top by writing private, writing the raycast hit data type and giving it a name short for raycast hit, such as RH. And the raycast hit variable is a very specific one that is used to extract information from whatever our raycast touches and will be what we use to find the tags we're looking for. For now, we simply need to tell our raycast in our function that we'd like to store any information it gathers into that variable we've created. Now, normally when using variables with commands and functions, we simply write the name of the variable into its parameter brackets. However, by doing this, we're actually telling our raycast that we want it to take information from our variable, when we actually want it to instead store information into it. So whenever we call a function or a command that we want to send data out rather than retrieve data to run, we simply write the out modifier in front of our variable, just like that. And a term modifier is used to describe words we can use, such as out, that change how we use certain fields, like our hit variable in this case. You can find a link under this lesson with more examples of modifiers. So that's all of the mandatory arguments our raycast needs. If we left our script like this, it would work perfectly, but for ours to work effectively for our desired purpose, we're going to need to add 2 more optional arguments. And the first requires a float value, which will be used to determine how far the raycast will travel. Now, as I mentioned earlier, we already gave ours the information with our directional vector, hence why this part is optional. But if we do add a float value here, it will essentially be multiplied by the directional vector to give it a new distance to travel. Now, because the player is so close to the ground when running, we don't need this raycast to travel very far. So let's create a new float variable at the top. We'll call it distance and we'll give it a value of about 0.3. Now, obviously, by giving our variable a value less than 1, we're essentially shortening how far it could travel. So that -1 we have set in the y-axis will now be multiplied by 0.3 and become -0.3 instead. So let's quickly add our new variable to the raycast function. Now, the last argument we can give our raycast is another new variable data type that tells the raycast to only gather data from objects belonging to certain layers. We've already talked about how layers are a way of organizing our game objects in the Play One-Shot lesson. Well, it's here where we can actually check those layers for specific game objects. First, we need to create another new variable, this time a public one of the layer mask data type, and call it LM for short. Let's then add this new variable as the final argument of our command. And we need to decide which layers our layer mask variable will tell our raycast to take an interest in. And because we made it public, we can very easily do this from the Inspector tab in Unity. So let's quickly save our script so we'll be able to take a look at it. Now that the script is compiled, you'll notice our LM variable has appeared as a drop-down menu. If we open that menu, we get a whole list of layers we can select. Now, I know that for this scene, we are only interested in the environment and the water geometry layers, as the majority of the surfaces LM runs on belong to one of those 2 layers. For example, if I quickly click the terrain in our scene, you can see it is a part of the environment layer. So in our menu, we're going to select both environment, then we're going to open it up again, and we're going to select water geometry. Now, whenever we fire our raycast, it will only check objects for their tags if they belong to either of those 2 layers. Now, this is very important for us, as there are many objects on top of some of the terrain that belong to other layers and don't contain tags. If we were to check these objects for tags, it would cause the material of our footsteps to change unintentionally and sound very messy. But with that, that's everything we need to tell our raycast to work. And before we move on to detecting our materials, we're going to quickly look at a way we can check to see if our raycast is being drawn in the correct direction and position we want it to be. To do this, we're going to write debug.drawRay with 2 brackets inside of our update function. So just like how we can write debug.log to send messages or variable values into our console, we can use drawRay to draw our raycast inside the scene tab in Unity. This will allow us to see our raycast while still keeping it hidden from the player as they play the game. Before we see our line, we need to feed our drawRay command some of the same information we gave our raycast. The first argument we need to give it is a vector representing where the raycast will start from. So let's add transform.position, just like we did with the raycast. Next, it needs a direction and a length given to it all in one argument. So just like how we learned that our raycast takes our distance variable and multiplies it to our direction vector automatically, we need to do the same here, but manually. So let's write vector3.down multiplied by our distance variable. Finally, we now need to choose a color for our line. To do that, we need to write color, follow it with the dot operator, and then choose from one of the pre-programmed colors. So I think I'm just going to choose blue for mine, but feel free to choose another color from the list. I'll also have a link under this lesson so you can check out all the colors. Great, so now a blue line will be drawn every frame from wherever our player is standing down towards the ground. Let's quickly save our script and see what that looks like in Unity. So now that we're back in Unity and we've got our scene running, we can click on our Ellen game object and scroll down to underneath her feet in the scene tab. And if we zoom in a bit, we should be able to find that line we created. There we go. So it's this line here. So here is the blue line we created, and because we're running this line in our update function, we can move our player around the world and the position will update to Ellen's new position every frame, giving us a clear idea of what our raycast is doing in the game. As we can see, it comes into contact with the ground quite nicely. It's also important to note that both the raycast and the debug.draw ray line will start from the game object center, represented by the axis arrows that appear when we click on a game object. So these arrows here. Now luckily for us, the model of Ellen has been positioned so that the center of the game object is actually below it and underneath her feet, meaning our lines are likely to touch the surface she runs on before any other object. So now it's time to check for our materials. At the moment our raycast is being drawn on the frames where our player takes a step. But other than drawing the line itself, our code isn't really doing much with it. An easy way to create behavior based off of a raycast is to simply put it inside of an if statement. So to do that, we're going to quickly highlight our raycast. We're going to press Ctrl X or Command X to temporarily cut it, then create our if statement, and inside the brackets, hit Ctrl V or Command 3 to paste it in. Also remembering to remove the semicolon that came at the end of the line. So now whenever the material check function is called, our code will check to see if our raycast is able to hit anything within the requirements that we've set for it here. And if it does, then it will perform whatever result we tell it to. Now here is where we can start checking for those tags we created at the beginning. So we now want to check which object our raycast touches and what tag it has been labeled with. This is where our hit variable comes into play. Now remember, it's through this variable we can check for information about the object the raycast hits, including its tag. Just like how in our first parameter lesson, we accessed our object's name by checking it through the collider component, we can tell our hit variable to do the same here. And we're going to want to check this condition inside another if statement, because if it finds a material tag, we then want our code to change the value of our material value variable to match the material that we set for it in FMOD. So we're essentially saying if our hit variable hits a collider, check the object's tag for, let's say, the earth tag, and if it matches, change the material value variable to 1. So let's write if, in brackets, rh.collider. Now we can follow this up by writing .tag and then using the two equal signs comparator to compare this condition to the tag we're looking for. But Unity actually has a command called compare tag specifically for this reason. So it's up to you which one you choose. I'm going to go for compare tag just to demonstrate it. And inside the compare tag brackets, we need to write the name of the tag we're checking for. Before we do, however, in order to save our code from creating new string data each time we call this function, we're going to create 4 string variables, which each containing the name of the tags we're looking for. So in our class at the top of our script, let's make some space once again. Let's write private string, call it E, short for earth, and then feed it the name of our tag as string data, which we know was earth. Let's then copy this line and then let's paste it in 3 more times, changing the name of each variable name and its value to represent the rest of our tags. So we're first going to do stone, puddle, and finally grass. Now we have all of our strings ready, let's add the first one, our E variable, into our compare tag command. So let's put our E there. Great, now all that's left for this if statement is to tell it to set our material variable to 1 when it finds its condition to be true. So underneath it, let's quickly write material value comes 1. So to quickly recap, our material check function will fire out a raycast down towards the ground. If it hits a game object that is not only within a specific layer we designated to check for, and has a tag that matches the value of our E string variable, our material value variable will be set to 1. Now all we need to do is tell it to do the same thing for the other tags. Now obviously we don't want our material variable to change if the condition inside our if statement is true. So we will use the else if statement to change the variable this time. Now remember that the condition inside an else if statement will only be checked if the condition inside the if statement above it returns as false. So in other words, if the tag isn't earth. So inside our else if statement, let's write the same thing we did for the if statement, but change the tag we'll check for to stone. So we'll write rh.collider.compare tag then in brackets, S, which is the name of our stone variable. Now you remember in our FMOD event, for the stone footsteps to play, our material parameter had to be set to 2. So we're going to do the same thing in our script. We're going to set the material value variable to 2. Let's then repeat what we've just written for our last 2 tags, and we'll have all of our tags covered. Awesome, we're nearly finished with our function. Now for a quick question. What do you think might happen if our player walked across a surface that was untagged or had a different tag to the ones we've created? For example, in this case, the terrain the player is currently standing on is tagged, but the stone stage in front of her is not. So if the player was to run forward, they would just continue to hear the puddle sounds, meaning our material value variable has not been changed. The issue here is that we now sound like we're running through a puddle even though we shouldn't be. So this is important to consider in case we forget to tag a surface or our player somehow finds themselves out of the bounds our game developers set for them. So to prevent this, we need to set our material value variable to one of our materials when none of our tags have been recognized. So underneath our last else if statement, we're going to write an else statement. Remember, an else statement will run whatever we tell it to if all of the other conditions inside the statement above it return false. So if this were to happen, I'm going to set our event to play the earth footsteps by setting the material value variable to 1. This is because it's a fairly natural sounding material that could be interpreted by the player listening to the game as another material, and it's also probably the most common surface throughout the game as well, meaning that the object that hasn't been tagged is more or less likely to be the earth. And we can also do something similar with our original raycast. If our player finds a game object to run on that our raycast doesn't recognise or can't gather information from, which could happen if, for example, the object is part of a different layer, then we need to make sure that the same issue doesn't occur. So now, underneath the if statement containing our raycast, we'll write another else statement, and again assign the material value variable to the value of 1. Now the last and final thing we need to do is tell our parameter inside FMOD to change whenever our variable changes. And to do that, we're going to make some space in our runPlay event function in between where we attached our instance to our game object, and just before we play the event, we're then going to reference our event instance variable containing our event and tell it to set the parameter material to match whatever value the material value variable is currently at. And just like the trigger parameter we used for the teleporter in the first parameter lesson, we want our parameter to change value instantly. But we also didn't change the seek speed option from its default inside the parameter in FMOD, which is also instantly. So it doesn't matter which Boolean value we give it here. So I'm just going to write false and then end the line with a semicolon. Now, as a little extra way to check everything is working as it should, back inside our material check function, when our raycast is called, we can write debug.log into this function, and inside its brackets, we can write raycast_hit.collider.tag. We can also add a plus sign and reference our material value variable as well. Now this will allow us to check if our material check function is successfully recognizing the correct tag, as well as what parameter value it is changing to when it does. And with that, we're good to go. Whenever we call the play run event function now, we'll also be calling the material check function, casting a raycast that will change the material value variable whenever it recognizes a relevant tag, which will in turn change our parameter's value. The only thing left to do now is save our script and test it in Unity. So now, if we start to run around the terrain, we can hear the sound of our player running through puddles instead of dirt. We can also see in our console tab that the raycast recognizes the puddle tag we attached to the terrain, and that our function has changed the material value variable to 3 as a result. If we then run over to the steps and the platform, we can both hear and see the stone footsteps. Finally, if we run over an object that hasn't been tagged, we can hear our parameter change to the earth footsteps, which, whilst we could change while adding the stone tag to this object we're running on, it does act as quite a nice stand-in. We We can also see that in the console tab, our debug.log command has recognized the object as untagged and has changed the parameter value accordingly. Great, so now we've seen multiple ways we can use the .setParameterByName command in code by passing data and variables through it to change our parameters. We now know how to use tags and layers to separate and search for specific game objects in our scenes. We also have a method we can use for implementing a material changing footstep system for animated characters in games. So well done if you were able to get all of that working. Take some time to take all of that information in, maybe rewatch this lesson, and then take a well-earned break because you've definitely deserved it. And feel free to experiment with more tags, more objects, and even more footstep sounds if you're able to record some of your own perhaps. Experiment with what you can and can't do, both with the game world and the code we've just wrote. Maybe you can find a simpler way of changing the parameter or want to just adjust the script to work with multiple parameters as opposed to just one.